Well, thank you. Thank you for the invitation to speak here. It's a big pleasure and a great honor. So yeah, I want to speak about my work on torsion in the homology, or cohomology, it doesn't really matter, of locally symmetric spaces. And in fact, I think the first two lectures I will just spend them on explaining what the statement of this result is. And so in fact, the general plan of the lectures will be that in this first lecture, give some general introduction. And in the second lecture, I will really explain the statement and give an explicit example for what this says. And I guess for the experts, it will only get interesting really in the third lecture, where I will try to give some idea of the proof. Okay, so let me start by recalling some very basic Galois theory. So what number theorists are interested in are the rational numbers and also their finite extensions. So this amounts to studying the field of algebraic numbers inside the complex numbers. So this is a set of all, let's call them alpha, all complex numbers, such that there exists some polynomial with rational coefficients, so some x to the n plus all coefficients are rational numbers, such that alpha is the root of this polynomial. And some of the basic observation of Galois theory is that if you think purely in terms of algebraic equations, then there's no algebraic way of distinguishing a positive square root of 2, say, from a negative square root of 2. And so what this means is that if we consider what's called the absolute Galois group of Q, sorry. This means that if we consider what's called the absolute Galois group of Q, which is just the automorphisms of this field Q bar, so meaning those bijections which respect the addition and the multiplication structure, there are quite a few of them. So, and Galois showed how one can somehow match the study of the finite extensions of the algebraic numbers with the study of this big group. And so let me give a few comments about this group. So whenever I have an algebraic number, I can look at the orbit that's actually just a finite set. So why is this? So we know that if it's algebraic, then there exists some p such that p of alpha is 0. But this implies that the same equation is also true after applying any field automorphism. So if you take any element of this Galois group and apply it to alpha, then this polynomial will still vanish on this conjugate. And so this means, as P has only finitely many roots, at most n, the orbit has to be finite. And using this, we can introduce a topology on this Galois group. So that's the weakest topology, such that for all algebraic numbers, the map set sense gamma to gamma times alpha is a continuous map. But in fact, this takes only finitely many values, so asking this continuity property is equivalent to asking that for all alpha, the stabilizer of alpha is open, is an open subgroup. So this makes this guy a topological group, and as just a topological space, it's the Cantor set. Okay. Let me give one more definition and then an example. So if I have a finite extension of the rational numbers, finite just meaning it's finite dimensional as a Q vector space. Let's call it Galois. If it is stable under the action of this Galois group, so let's look at this in two examples. So let's first do this example of the square root of 2. So if k is the square root of 2, q adjoint the square root of 2. So concretely, that's just the set of all a times b in the square root of q, where a and b are rational numbers. Then if I let the absolute Galois group act on the square root of 2, then the orbit will be all possible roots of 2 inside the complex numbers. So that's the square root of 2 and minus the square root of 2, both of which are contained in k. And so this means that if I let this group act on k, it's Galois. And by the way, I should say that in this case, if it's Galois, one also has a Galois group of k over q, which is just the automorphism group of k, which is a finite group. So in this case, the Galois group of k over q is, say, the symmetric group in two elements via the action on those two elements. So the second example is if I decide to adjoin a third root of 2 to q. So that's the set of a plus b times the square root of 2 plus c times square root of 4 can check that this set is stable under addition and multiplication. So then, if I let the absolute Galois group act on a third root of 2, then the orbit will again be all possible third roots of 2 in the complex numbers, but now there are 3 of them. It's the third squared of 2. But you can also multiply it by a third root of unity, which is e to the 2 pi I over 3, or by this. The picture would be in the complex numbers, you have somewhere 2, here's somewhere 1, and then there's a third square root of 2 somewhere here, and then there are these other 2 guys here. And so obviously these elements are not contained in K, simply because K consists only of real numbers, whereas these other guys are not all real. But you can improve this. So, third example. So, if you take this extension and also add a third root of unity, so now this has a chance of being Galois, because now these other roots are also in there. And in fact, you can easily check that this is now really Galois. And now its Galois group is isomorphic to the symmetric group in 3 elements, again via the action on the 3 element set consisting of these 3 third roots of 2. And so this what Galois theory tells you is that you get a bijection between the finite extensions contained in Q bar and the open subgroups, let's call them H, of the absolute Galois group. Whereas associating any K to the set of all those alphas such that all those elements of the Galois group such that for all elements in K they don't act on it. So in other words, it's a subgroup which fixes K pointwise. And conversely, if I have a subgroup, I can associate to it the fixed vector under this open subgroup, which are all those alpha such that for all gamma and H, it preserves this. So in other words, this absolute Galois group is somehow a way of encoding all the possible finite extensions of the rational numbers. And a number field is Galois if and only if the associated subgroup is a normal subgroup. In other words, it's invariant under conjugation. And second part is that Q bar is actually the union over all finite Galois extensions. And so the absolute Galois group you can think of as the inverse limit of all such K of the automorphism groups of these finite extensions. So all of these are finite groups. And so this absolute Galois group is naturally a profinite group. Profinite just meaning an inverse limit of finite groups. And so, in other words, everything that I'm about to say about this absolute Galois group is really a statement about one of these finite quotients, but without specifying which finite quotient we're talking about. So, and so if you're trying to understand this profinite group, so it's an inverse limit of finite groups, and one way to understand it is to by understanding the maps to finite groups of Lie type, say. So meaning groups such as GLN of a finite field Fp. Because after all, almost all the finite simple groups, they are finite groups of Lie type. And so it's certainly interesting to understand all these quotients, which are such finite groups of Lie type. So, and these will play some more central role in these lectures. So, so for this reason, I will give them a name. So, a finite Galois representation is a continuous map rho from this absolute Galois group to some GLN P. And in fact, I might also allow bigger finite extensions of Fp, but that's a minor point. So in other words, giving such a finite Galois representation is equivalent to, first of all, so the kernel of rho be an open subgroup. And so in particular, this defines a field corresponding to rho, which is a fixed field under this H, a finite extension of Q. So really what you have to do is, first of all, specify this finite extension of Q. And it's supposed, and that there is this map means that its Galois group has a very specific form. It's essentially this finite group of Lie type, or maybe a subgroup of it. And so what I'm talking about in the series of lectures is the following diagram. So in the center, we have these finite Galois representations. And actually, one reason one might find them interesting is that there is a geometric way of constructing those. Namely, whenever you have a variety of a Q, so variety you can think of simply as a system of polynomial equations. Just some geometric object which is cut out by polynomial equations with rational coefficients, and by some black box called état cohomology, which I will explain later in an example, one can go from there and produce some finite Galois representations, which, remember, a surprising lot of information about this geometric structure you have here. And on the other hand, there's a completely separate way where these finite Galois representations occur, which is in some sense much more mysterious. So, namely, that's some of the topic of these lectures, in the torsion homology of locally symmetric spaces. So for some rather mysterious reason, A, this also gives rise to finite Galois representations. And in fact, there's a conjecture that called Sayre's conjecture that actually everything comes from the torsion homology of locally symmetric spaces. So there are somehow two big problems in this area. The first thing is this torsion homology actually gives rise to Galois representations, finite Galois representations. And then there's a second, much harder problem, which I want to say nothing about, called Sayre's conjecture, which is that with a very small caveat, so only almost, but it's really a very small thing, all finite Galois representations occur in this way. Aha, okay, so I mean A is now a theorem and B is far from a theorem. So and in any case, somehow in the classical case of GL2 over Q, A was very easy and B was very hard. So. And so what I will do today is just explain why such a statement would be interesting. I mean, I should say that these lectures about A. Okay, so let me do this very famous example. So for now, let's start with just with an elliptic curve. So let E over Q be an elliptic curve. So what does this mean? So it has a zero section, just a point called 0. And the complement of 0 can be written as this set of solutions to the following equations, just a cubic equation, two variables, which can be brought into the standard form, so where A and B are just any rational numbers satisfying that the discriminant, which is probably 4a cubed plus 27b squared, is non-zero. So it's certainly very easy to write down such objects. And they're of immense interest to number theorists. So if you draw the real points of this elliptic curve, then draw the x-axis and the y-axis, then there's this famous picture of some bubble and some such line. Well, not line, but anyway. And then there is off at infinity this point called 0. Oh. Unfortunately, it's called 0, but anyway. And so it turns out that E of k is naturally in a Abelian group with 0 given by this point called 0. That's why it's called 0. For any characteristic 0 field k. And so in this picture, you can see the group structure in the following way. So if you have a line which intersects this cubic in 3 points, P, Q, and R, then what you demand is that P plus Q plus R is equal to 0. Okay, and so if you look at the set of solutions to this elliptic curve over the complex numbers, then you can find out that as a topological space that's actually homeomorphic to donut. Or a different way of saying this is that it's a C modulo a lattice lambda, where lambda is isomorphic to Z2 and C is a lattice. So the picture is that you have such a lattice and identify opposite sides, and then some extent is. So you fold these two lines together and the other two lines together, you get this. And so this implies the following. So for any field E, k, let k of n, let ek brackets n denote the kernel of multiplication by n. Then if you look at this over the complex numbers, then you see that, say, if n is 3, then the 3 torsion points are these dotted points here. Or another way of saying is that there's the points in 1 over n times lambda modulo lambda. So just abstractly, this is as an Abelian group, it's Z mod nz squared. But these n square points are solutions to an algebraic equation, simply because all the structures on this elliptic curve are given by polynomial equations. And so this means that all of these a priori complex valued points are actually algebraic numbers. And so the n torsion of this elliptic curve over Q bar as in the Abelian group is just Z mod nz squared. And so the absolute Galois group naturally acts on these n torsion points because it acts on the algebraic numbers. And so say if you take n equal to p a prime, then what this gives you is something we might call rho EP. It's a map from the absolute Galois group into the automorphisms of this p torsion group. which is just GL2 of Fp. So you somehow started with this interesting geometric object, and using the torsion points in this elliptic curve, you have cooked up a Galois representation. And that's actually a special case of this very general machinery called étale cohomology. Yeah? And now let's specialize a bit further. And so let P be a prime at least 5. And let's look at a solution to the equation a to the b plus b to the p plus c to the p equals 0, where a, b, c are non-zero and integers. And of course, we want to show that there are no such solutions. So an idea put forward by Frey in particular, but also I think by other people like Galois, I don't know, was to study this by looking at the following elliptic curve. So the elliptic curve looks like the following. So it's x minus x times x minus a to the p times x plus b to the p. That's not exactly in this form, but it doesn't really matter. Everything works the same. And so if you look at the pairwise differences of the zeros, then, of course, if you look at the difference here, it's a to the p. If you look at the difference between those two, it's b to the p. But now if you look at the difference between those two, it's the sum of a to the b and b to the p. And by our assumption, that's again a piece power. So this implies that the discriminant is actually a piece power, which is somehow key to the following arguments. And so now what we do is we look at the p torsion for this very same prime p that we used up here, which is now a map to GL2FP. And it has some very good properties. Namely, I will not say precisely what this means, but it's very little ramified. So it's unramified outside 2 and p, and has very little ramification at those primes. And then Sayre conjectured that in this case, rho AP has to arise from a modular form of way 2 and level called gamma naught of 2. I will say later maybe what precisely this means, but it's somehow an instance of this conjecture that any finite Galois representation should arise from the torsion homology of locally symmetric spaces. And we can say precisely where it should appear. But here the observation is simply that there are no such modular forms. So for this reason, rho EP cannot exist. Which implies Fermat's last theorem. And so this is what Wiles and Taylor-Wiles proved. And actually, you also use the theorem of Ribbit, which tells you that actually you can find it exactly there. So the principle of this machinery is that from very general geometric situations, you can produce via Talc homology these finite Galois representations. And from the geometry, you also know where they should appear in the torsion homology. And then you can just do a computation whether there is anything there. And if there is not, then some of these geometric situations that you're contemplating cannot exist, actually. And so before going on, let me also say that I've mostly worked with the absolute Galois group of Q, but actually something similar should work for any finite extension of Q. Let me draw again the diagram. So now in the middle you have the absolute Galois group of K, which is just those field homomorphisms of Q bar which fix K pointwise going to some GLN. And then by a Talc homology, you can now build such guys for any variety whose defining coefficients are in this field K. And again, there should be this connection with the torsion homology. Locally symmetric spaces. For the group GLN over this field K. And in my lectures, I will discuss two cases in detail. So the first case, which is classical, is the case where n is 2, and I'm really working over the base field Q, which is somehow where this example fits in. And in the second case, n is still equal to 2, but I enlarge my field and I take Q adjoins the imaginary unit. So I might also consider still K is Q and bigger n, but then there are very large dimensions, these examples, and it's hard to make things explicit. So I'd rather stick to this different example. And so today I want to start with explaining what happens for GL2 over the base field Q. So that's the business called modular curves. So what do we have here? So the basic object in this case is the complex upper half plane. So all those complex numbers whose imaginary part is positive. And if I write tau as x plus iy, then this carries a natural hyperbolic metric by this formula. And so you can also regard this as two-dimensional hyperbolic space. And as a group of isometries of H2 as a two-dimensional hyperbolic space is a group PSL2 of R. And so if you have a matrix ABCD in there, then it acts by sending tau to this fractional linear transformation A tau plus B over C tau plus D. Okay, and then what I do to get arithmetic into the picture is that I take a congruent subgroup of SL2 of the integers. So this means that gamma contains a subgroup of those matrices which are the identity modulo some large number n. So in other words, it's a subgroup given by congruence conditions on the entries. And then I can define the modular curve, which in this case is this locally symmetric space I've been talking about for GL2 over Q. So it's just the quotient of this two-dimensional hyperbolic space by the action of this congruent subgroup gamma. And so again, I can draw this. If gamma is SL2Z, then you have this famous picture. So you have somewhere 0, somewhere 1, somewhere you have the imaginary unit, somewhere you have -1. And then if I draw these straight lines and I draw some circles, so here's 1 minus 1 plus I, here's 1 plus I, here's some, let's call it rho, and here's some rho squared, where rho is the 6th root of unity. Then this area here is a fundamental domain. Which thus essentially represents this quotient. And you see that there is something strange going on at these points I and rho. So I and rho are orbifold points. Meaning that there is a finite subgroup of gamma which stabilizes these points. But if I pass to a sufficiently small subgroup, then this gadget will actually be a two-dimensional hyperbolic manifold. So it has a canonical complex structure. So you can also observe that of course, the complex upper half plane has a canonical complex structure, and the action of this group is by holomorphic maps. So this holomorphic structure will descend to this quotient. And a very basic theorem about these modular curves is that actually they are algebraic objects. So H2 mod gamma has a canonical structure as an algebraic variety, or even curve. So if you take a one-dimensional gadget and take its complex points, it's two-dimensional as a real object over C. So it's a set of solutions to some system of polynomial equations. And in fact, at least if gamma contains a subgroup gamma 1 of n, which are those gamma which are congruent to star star 0, 1 mod n, which is not a real loss of generality, then it's this gadget is actually defined over Q. So it's actually it's the set of solutions to a system of polynomial equations with rational coefficients. So it's a priori it's just some kind of real manifold, but then it gets more and more structure, and eventually it's some very number theoretic object. And so it's a very old theorem. I'm not sure who exactly proved this, but it relies on the interpretation of the space as a moduli space for elliptic curves.
Is it explicit for any for small n?
For small n, you can explicitly write down the equation, yes. Yeah, I mean, it's just one equation and 3 variables. I mean, it's really some very nice equation. And so if I go to larger level, so if I not contain such a subgroup, then it's still defined over finite extension, finite explicit extension of the rational numbers.
Sorry, what is the exact statement? Because if you take any gamma which just contains gamma 1 of n, is it still defined over Q? I mean, there are tons of those gammas somewhere between the whole group and gamma 1.
Well, in general, you should take some finite disjoint union of such guys, and it's defined over Q. So you should really adopt the eidetic viewpoint in which you take a finite disjoint union of such guys.
So the statement as written is not right.
I think it's right.
It says that if gamma contains gamma 1 of n, then the quotient is defined over Q.
I think that's true.
And somewhere between the big group and the congruent subgroup, there are not a single.
It contains gamma 1.
Yeah. So if you make this upper star smaller, then you will make the base field bigger. And so, I mean, these lectures are about the homology of these objects. So let's talk about homology. So, because this is an algebraic curve, you know that its homology groups are actually torsion-free, and 0 if I is bigger than 1. And so some of this torsion cohomology I've been talking about all the time is really the homology group of this locally symmetric space with coefficients in some finite field Fp. And so in this case, you can really just compute this as a homology with integer coefficients and then modding out P. Well, it's not compact. So. I mean, there are some points at infinity missing. for every p. Well, I assume, I guess, that gamma is sufficiently small. Otherwise, I might have to exclude 2 and 3. Okay, so in this case, the mod p cohomology is really just a reduction of the integral homology. And on the other hand, Hodge theory tells you that if you consider the homology with complex coefficients, which again is just the base change of the integral guide to the complex numbers, then this can be described in terms of certain harmonic functions on this guy. And so in this case, it's really just way 2 modular forms. So recall that in Sayre's conjecture, it was postulated that there should exist some way 2 modular form, which should give rise to this Galois representation. So it's some element in here, essentially. But because this is torsion-free, there's a very tight link between this guy with the complex numbers and this guy over Fp. So they are vector spaces of the same dimension, for example. And so because of this, in this case, Sayre's conjecture can be reformulated. In terms of this torsion homology. And this actually turns out to be the point of view that generalizes well to other groups. So to bigger n, for example. So how do you formulate Sayre's conjecture here? So the remark is that because this guy is such an algebraic variety over Q, again, by this black box called étale cohomology, there is a natural Galois action on this homology group. And so you see that in this case, there is a very tight link between this torsion homology group and Galois representations, namely the Galois group just acts on it. So it's somehow obvious that any torsion you might have here will give rise to Galois representations. And so Sayre's conjecture, in this case, can be reformulated as saying that this gadget rho P that we considered earlier occurs in as a Galois covariant subquotient. And this non-existence of weight 2 modular forms in this case simply said that this group is 0, but then because it is torsion-free, this guy has to be 0, and this torsion homology has to be 0. So nothing can appear there. So in this very action here, this provides the link between torsion homology and Galois representations here in this case. And so I guess time's up. So next time I will explain what happens in the second case I want to talk about, so where n is 2, but now this field is an imaginary quadratic field. And so in that case, this 2-dimensional hyperbolic space will become some 3-dimensional hyperbolic space, and things will turn out to be very different.